Okay, we probably should get started so we can all get out and have dinner at a reasonable hour tonight. This is a great turnout. As many of you probably know, the Emiliani lecture series was initiated last year with the inaugural talk was by Nick Shackleton, and this is the second time that the Emiliani lecture is being held. As many of you can see from the overhead, this is Cesare Emiliani in his heyday. He was really truly a visionary, probably one of the founding fathers of the field of modern paleoceanography. And the other day I was at my office trying to reflect on how to start this introduction, and I went to my library and found some of Cesare's original publications. Rob, do you want to just turn the overhead on? And I find it only ironic that when you take a look at his 1954 paper and his 1955 paper, trying to figure out what Pleistocene temperatures were like and trying to figure out what the depth habitats of foraminifera were using oxygen isotopes, that it seems like after 45 years we haven't come a long way. Okay. But today's speaker attests to the fact that we have come a long way. And it's my pleasure to introduce Jim Kennett, professor at UC Santa Barbara. Jim's CV is an enviable document. Jim, you can shoot somebody at the office there. They faxed it to me. And so this is a very brief summary. Jim told me to keep this to 2 minutes. First of all, Jim's a fellow of the American Geophysical Union, the Geological Society of America, AAAS, and earlier this year he was became a member of the National Academy of Sciences. He's published more than 200 papers and written or edited three books and 17 volumes. And by the way, Jim, marine geology really needs to be revised. He's also was the founding editor of the American Geophysical Union journal Paleoceanography. For the last 35 years, Jim's research has been opening doors and making discoveries that have contributed greatly to our current understanding of ocean history and climate change. Much of his research, for 20 years or more, focused on the understanding the development of the cryosphere, the glaciation of Antarctica, and ocean circulation during the Cenozoic. I had the privilege in 1989 and 1990 of being at UC Santa Barbara at the Marine Science Institute and sharing on the discovery of the LPTM, the late Paleocene thermal maximum, which we all know now is, or we think it's methane clathrate driven. And I think that it was that PE boundary event that probably brings us to where we are today, after Jim's also made some astounding discoveries in the Santa Barbara Basin and ODP hole 893 of periodic methane bursts and the potential impact on climate. So I think I'll stop there, and please join me in welcoming Jim Kennett, who will be speaking on the role of methane hydrates in lake quaternary climate change. Jim.
Thank you for coming. Indeed, nice to see you here. I wanted to start by saying that Cesare Emiliani was trained as a micropaleontologist in Bologna, Italy, and just after the Second World War, came to the U.S. and, of course, did this classic work on stable isotopes as major proxies and paleoclimatic changes in the Quaternary. But he never lost his interest in micropaleontology, and in fact, he wrote a paper. He never held back on titles. He published a paper called "A New Micropaleontology in the 70s" that some of the older fellows may know here, remember. He never lost his interest in foraminifera, and in fact, at his death, I was actually writing a paper with Cesare on processes in evolution of planktonic foraminifera. Unfortunately, it's a paper that has never been completed. and it's an honor to be here representing the memory of Cesare Emiliani's work. Today's talk is the role of methane hydrates in the late Quaternary climate change, the clathrate gun hypothesis. And the collaborating authors are Kevin Canariato, Ingrid Hendy, and Rick Bell. Now, I've just come back from Canada. I've been up there on sabbatical for 6 months, and at the University of British Columbia, amongst a number of colleagues, I won't mention them all, quite a few. It's a very nice group. I've enjoyed that experience. I've been basically up there with the Canadians looking for clues. And looking for clues, that's Tom Pedersen there in the middle. That's Kennett on your right. And basically what we've been, many of us, of course, are doing is trying to understand, looking for clues as to what on earth caused this remarkable behavior in Quaternary climate change, in late Quaternary climate change, especially during the 100,000-year world, the last million years or so. Trying to understand the mechanisms, the processes that give rise to, for instance, this kind of pattern as recorded in the Vostok record, but it's also, of course, recorded in marine sediments, where you have these rapid prolongations of warmings in the order of just decades, as shown by the ice core work, just decades, where you actually jump in state from a glacial to a near or interglacial state in just a few decades. It's just remarkable behavior of global climate that's been discovered in the last decade or so. So what are the causes of that? What are the causes of this rapid warming, the initial great warmth, beginning of each of the glacial cycles in the 100,000-year Milankovitch? Why is there a decrease in temperature through the glacial cycle? Why is each cycle terminated by the most prolonged and coldest conditions, and then immediately juxtaposed by another rapid jump in warming? This is quite remarkable behavior that many of us, of course, are dying to know about. Well, not death, I hope, but certainly interested in knowing about. And of course, then we also have as we all well know, the pulses, the flickering at millennial and decadal scale in the last ice age, the so-called Dansgaard-Oeschger cycles every 14 or 15,000 years, which give rise to these interstadials and stadial oscillations, and like the 100,000-year cycle, each one seems to begin with a very rapid jump in warming, the order of probably a few decades, and then a sort of a more slower cooling, leading to this sawtooth pattern that marks the Dansgaard-Oeschger cycling. These are major questions that require explanation, this kind of behavior, the kind of sawtooth pattern that occurs in the 100,000-year world of the Milankovitch oscillatory behavior and the millennial or sub-Milankovitch behavior. Now, these Dansgaard-Oeschger cycles have since been discovered in numbers of areas of the world and marine sediments and throughout different regions where, in fact, there are high enough resolution records, such as in Santa Barbara Basin, some work that we've published earlier, where the Dansgaard-Oeschger cycles are very well expressed and show near synchronism, it seems, with the climatic changes, the large, rapid climate changes that were first recorded in the Greenland ice core record. And just published, you have these appearing in these high-resolution records wherever there seems to be a really exquisite chance of recording atmospheric signals. You seem to get this beautiful matching of records as shown in the recent just published work by Larry Peterson and Conrad Ewan and others, the colleagues there, in the Cariaco Basin, which indicates that the Earth, at least large parts of the Earth's surface, are undergoing this kind of cyclicity, this kind of climate behavior, as long as you are recording an atmospheric signal. Now, the other aspect that's very interesting is the close association that occurs between the oscillations in the temperature record, as shown here in this Bostock, here for the last 400,000 years, the temperature record here, and the greenhouse gases of methane on the lower one and CO2 in the upper one. They're very familiar records for virtually all of you. So you have this intimate relationship in greenhouse gas oscillations with climate, at least at this time scale, it seems. And again, major rapid warmings associated with rapid increases in atmospheric methane and CO2, and so forth. Just a nice match, especially between the methane and the methane oscillations and the climate or temperature records here. CO2 is closely related, but the coolings are associated with more gradual decrease in CO2, as it seems in that record. So these are very interesting observations that need explanation in terms of what the sources of the greenhouse gases are, and particularly in this case today, what the sources of the methane are or were. Likewise, at the millennial scale, some beautiful work done by Ed Book and others in Severinghouse for the Greenland ice core at higher resolution. Again, a similar kind of behavior at the millennial decadal scale with this, an association between the methane jumps, these rapid major methane jumps, in close association with the with these rapid climatic flickerings during the last ice age. Now, the major question, of course, or major question in my mind, is where on earth is this methane coming from? Why does the methane rise so rapidly in the order of decades to a few hundred years, as shown in the ice core record? And is there a relationship any relationship at all between the increases in methane and the changes in the climate? Now, the general consensus, the prevailing consensus, certainly the major consensus, is that these kinds of rapid rises in methane that are shown in this Greenland record for the last 20,000 years here, this is methane, these rapid rises are derived from, the rapid rises of methane are derived from the increased production and generation of wetland systems and the associated methane from continental wetlands. So that is the prevailing consensus hypothesis. So let's just look at the general budget of the pre-anthropogenic or natural sources of methane in the global atmosphere, and this clearly shows that the wetland in the modern pre-anthropogenic system is dominated by methane from wetlands, which is kind of split between methane generated in tropical wetland systems and in the northern high latitude wetland systems. But there are other sources such as termites, ocean and freshwater sources, geological or natural gas seeps, and ungulates or bobbids, biomass burning. But as you can see, the major player here is, in terms of the modern late Holocene, is from wetlands. So it's not illogical that the prevailing consensus for the explanation of these jumps in methane are the result of an increase in wetland production of methane. However, this mechanism requires a rapid development and response of wetlands to be an important methane source. That's a given, because given the behavior of the rapid rises in methane at the glacial terminations and the onset of the Danskaruska interstadials. However, I'd like to now go through some information on wetland evolution of wetland systems and point out that wetlands, and I've been doing a lot of reading on this during my sabbatical, is that wetlands are complex ecosystems. They require a lot of time to form. They don't form rapidly, and the methane generating capacity of wetland systems is not an instant response. You don't expect it to be an instant response in times of global climate change. Now, there's a very large literature on peatland and wetland formation and the change in the nature and requirements of methane production. It's a very large literature. I've read some of it. I've talked to a number of specialists on this. But I would say that the literature supports the concept of slow growth and not of punctuated development of methane-forming wetland systems for the origin of these jumps in methane. The great modern wetland systems, in a word, formed during the Holocene. The 15% of the continental areas that are now characterized by wetlands in the earth, very large areas, all formed, as far as I can tell, during the Holocene. They formed gradually during the Holocene, and most of them formed during the middle and late Holocene, after sea level rose to its more or less present-day level. Let's look at some of this data. I'll go through this quickly, because I have two parts of this talk: wetlands and then the gas hydrate hypothesis, or the clathrate gun hypothesis. This overhead shows the present-day distribution of mires, peatlands, swamps, bogs, and so forth. And you can see that they occur in two belts, the high northern latitudes and the tropics. And I've superimposed on this the position of the ice sheets during the last glacial maximum, which clearly shows that most of the greatest proportion of the high latitude northern wetlands were not available to form methane during the last ice age and during the glacial terminations. They simply were covered in ice. So that's the first point. Now the second point is that we go to the paleobotanists, and this is some work done by Adams and published in Nature in 1990, where they show the distribution of vegetation belts during the modern and compare it with the last glacial maximum. Not to dwell on this very long because there's insufficient time, but the main point is that during the last glacial maximum, the Earth was really very dry. It was marked by obviously large areas of ice, larger areas of deserts, much larger areas of grasslands, of polar deserts, and of generally drier kinds of vegetational landscapes compared with the present day. There was, in the conclusion of Adams, they found no reason to have any peatland ecosystems during the last glacial maximum, as compared with the very large peatland contribution to organic carbon in the modern world. And having read a lot of the literature, I would have to agree with the conclusion of Adams that there were very limited wetlands or peat-forming systems and other kinds of wetland systems during the last ice age, and in fact during the last deglaciations. I'm going to quickly go through, without showing you a lot, without going over the details, the timing of the wetland development in different areas of the world to make this point. At the high latitudes, Canada and Russia, Siberia, the modern wetland systems of the last glacial cycle have exclusively formed, or near exclusively formed, during the Holocene, as shown by those numbers. I'm going to go quickly through these. I don't expect you to read the details. And now there are two areas in the high northern latitudes. There are those that were covered by ice sheets, and there are those such as areas of modern great peatland systems, like in Siberia, that were not covered by the ice sheet. Now, if we take the continental western Canada, which was an area covered by the ice sheet, the Laurentide ice sheet, and this is the work of Witt et al., Canadians, they show that following deglaciation of the Laurentide ice sheet, there was a very slow initial development of peats, and then a steady production of peatland systems, and organic carbon deposition accumulation, mostly during the middle and late Holocene. And the upper graph shows simply that as with the increasing age of peatland systems, there's obviously an increase in thickness of the peatland systems. They grow quite slowly. Now, this is some work from Harden et al. In 1992, and again, that reinforces the previous concept, whereby you get deglaciation or exposure of land masses, and then that was followed rather slowly by the accumulation of peats themselves. And most you can see in this is an area covered by the Laurentide ice sheet. Most of the peats formed in the middle and late Holocene. Now, there was in EOS just a month ago. There was a publication on peat formation in Siberia. This was an area that was not glaciated, did not have an ice sheet, and so I plotted here timing of initiation of peats and the various cores, of 41 cores I think they studied in that study. And the peats began to form only about 12,000 years ago, and then steadily grew expanded in their distribution in this area of the Ob River in Siberia. And I plot against that the methane curve, just as an example of, or comparison of the methane oscillations during the last 18,000 years versus this particular development of this particular peat system. And again, here is a peat system that unfortunately I don't have it's a fairly large one. I don't have a scale on here. It's a schistic peatland in western Siberia. It's mapped by the Russians, and they show in the green the development of wetlands and of associated peats during the Holocene. This is early Holocene. There's virtually none. Then you progressively develop the peats in this particular large peatland system. So much of it occurred during the middle and late Holocene. So that's the high latitudes. If you take the middle latitudes of, say, North America, if you just take the Everglades, which is a small system, the peats there began to accumulate about 5,000 years ago. Okay, let's look at the tropics. The tropics in South America, Amazonia, the timing of wetland development was again primarily occurring during the Holocene. Now these are not peatlands, these are different kinds of wetland systems, but they're large methane forming systems during seasonal inundation of the floodplains. It occurs seasonally and rapidly. And again, if you look at the paleobotanical, geological, and sedimentological data, these wetland systems of Amazonia developed during the Holocene. They didn't develop, and they developed gradually during the Holocene as sea level came up. I'm going to show you two different states of Amazonian conditions, the last glacial and the mid-late Holocene, or the modern system, for the last 6,000 years. And it's made the schematic diagrams just simply to compare and contrast the two states. Now, during the low standard sea level, the rivers were incised, and there was good geologic evidence that the Amazon River ran in incised canyons throughout most of its extent, including its tributaries, way back into the heart of South America. And this, of course, led to well-drained rivers as compared with poorly drained rivers, incised river channels rather than sedimented river channels. The sedimentation of the rivers occurred once base level came up as a result of sea level rise, and the rivers filled in. Now, those rivers are still filling in the Amazon. The Amazon Delta was actually relatively starved of sediment. A lot of that sediment is not getting out into the ocean. And they're still filling in areas of the channels that were incised during the last glacial maximum. In other words, it has not as yet reached equilibrium. There was dynamic flow versus sluggish flow, and so forth. And there was no flooding of plains. The paleobotanical evidence indicates that, as compared with extensive water and sediment entrainment and flooding of the plains, of the floodplains during the present system. There was negligible wetland vegetation during the last ice age, as compared with extensive wetland vegetation, including the agapo, or specialized forests that occur in these inundated wetland Amazonian floodplains. Low methane production, high seasonal methane production. Illustrate the evolution. This is coming from Bailing and others, and primarily and other work is paleobotanical work. They all consistently show that the early Holocene was a relatively active river system with flushing of the water out into the ocean and of sediments, and then a progressive damming or clogging of the system as the sea level came up, and you end up with these extensive seasonal floodplains in Amazonia. And this kind of evolution through the Holocene actually occurs not only in eastern Amazonia near the coast, but actually extends way back up the river systems into western Amazonia. You get a transition, for instance, in the Rio Negro from what they call white water to black water, and that occurs in the late Holocene. Much of the flooding is middle and late Holocene. Now, let's look at the timing of wetland development in the tropics. Southeast Asia has large peatlands, tropical peatland systems, and those occur in areas of Indonesia, Malaysia, Thailand, and New Guinea, and so forth. And I've looked at the research, and as far as I can tell, those major peat systems accumulated mostly in the Holocene, or entirely in the Holocene, and not in the pre-Holocene and the last glacial cycle. Now, Africa has been suggested as a potential source of methane at the deglacial periods. Africa is a relatively arid continent, and it does have some swampy areas, including very large swampy areas in the source of the Nile, where those major lakes occur. So I've looked there at the literature, and there's a recent paper, good paper or interesting paper by Bonifio and Charlet, just published recently this year, in which they have examined the evolution of the peat systems or the peat bogs in Central East Africa. And to make a long story short, basically they show that the Holocene again was a time of major development of peat systems, and as compared with the glacial period and the deglaciation. And furthermore, at the very time when you have this rapid rise in methane in the ice cores during the deglacial periods, beginning of the Booling, beginning of the Holocene, termination 1A, 1B if you like, I'll quote, alternating dry and wet climate or unstable climate at those times did not favor the formation of peat during the deglacial transition. Indeed, deposition of peat requires specific and stable conditions in temperature and humidity. And I'll show you the data. They looked at a number of peat profiles. This is simply the deposition rate of peat in this particular area of East Africa. And here's the pores of peat. And the pores of peat is actually, or peat accumulation, is actually over deglaciation. There's obviously peat formation before that, some peat formation during the glacial, but major and gradual formation of peat during the Holocene. Now, so just to simply point out here that that peat accumulation, just to emphasize that peat accumulation rates are really slow. These are some reasonable numbers from the high latitudes, so that in 100 years you'll form about 5 centimeters of peat. In the tropics, the rates are higher, but the initial formation of peat, based on the literature and talking with experts, is that there's not only a delay in peat formation at time of climate change, even favorable climate change, but there's actually the initial formation of peat is relatively slow, and then when the ecosystem gets going, it accelerates. So you end up with peat accumulation rates 5 to 10 centimeters in 100 years, and then from 10 to 20 centimeters in 100 years. These are not thick, huge methane-producing systems. Now, need I remind you that the modern river delta systems and their associated wetlands formed during the Holocene as a result of, according to Stanley and Warney, which I agree with, based on a study of 36 deltas around the world, the development of the river delta systems was caused by the deceleration of sea level that occurred in the middle Holocene. Now, so the point is that I don't see any modern system, any pre-Holocene peatlands of any extent that are that occurred prior to the Holocene. So, but the question is, are there any compensating peatlands that occurred, for instance, on the continental shelves or other areas, which will compensate for those that have formed during the Holocene, the middle and late Holocene, and hence be methane-producing systems? So I've looked at the literature on continental shelves, and I've talked to experts. And basically, if you look at Beringia, which is a potential major candidate in the high northern latitudes, according to Hans Nelson and others and their publications, the peats that do occur there, and they do occur there on the continental shelves that have since been inundated as a result of sea level rise, the peats are thin and scattered. They're not major sheet-like peat systems at all. And most of the peats, according to Elias' study, were occurring between 14 and 9,000 years ago. But they're fairly scattered and thin. So in eastern North America, actually Ken Emery wrote a paper in 1967 on peats on the eastern seaboard, and most of those began growing during the deglaciation. But again, they're thin and patchy. So let's look at the Sunda Shelf, and the Sunda Shelf is an area that has been considered by Tom Crowley and others as possible candidates for methane production during the low stands of sea level during the last ice age. And the Sunda Sea is a very extensive epicontinental sea. The Sunda and the Java shelves are very large areas in the warm pool of the Earth, present warm pool of the Earth. However, it is found that these areas were heavily incised, again, by sea level, by the river systems. There is evidence of channeling as a result of the incision of these. And I believe that the water table was relatively low, and the wetland systems did not form. But however, the mapping by recent mapping by Hannebuth, a PhD thesis in Kiel, shows that there is a near absence of peats and organic rich layers in the cores during the glaciation and during the deglaciation. In other words, there's no evidence from the study that this was a major compensating peat system for during the last when sea level was lower and the continental shelves were exposed. So this makes some quick summary statement of this, and we can move along. Okay, so there was rapid development and response of wetlands. Rapid development and response of wetland are required to be an important methane source. In other words, there has to be a rapid response of the system in order to get those rapid rises in methane. Wetlands are complex ecosystems. The production of methane from wetlands has critical requirements. These are very sensitive systems. There were limited wetlands and peatlands during the last glacial. And I believe that is the reason, or we believe that the reason for that is that it was because of low sea level and low water tables. The water tables are playing a crucial role in this process, and a general dryness of the earth. Increased rainfall alone does not produce methane. So you can increase the rainfall as a result of climate warming. That does not automatically produce major wetland system, methane-forming wetland system. I think that's a crucial thing to keep in mind. The development of the modern wetland systems occurred almost exclusively during the Holocene. This was slow, a delayed growth of modern wetland peatlands during the Holocene. It was slow and gradual, and much of it occurred in the middle and late Holocene. There appears to be no significant other peatlands at high latitudes or on shelves during deglaciation and the last glacial. So what we argue, therefore, and I go to the second part of the talk, is that there has to be another source of methane that causes these very rapid rises in the methane as measured in the polar ice cores, in the bubbles of the polar ice cores. This is obviously the other major source, potential source that can do the work, as far as we know, are gas hydrates that are basically frozen methane incorporated in marine sediments. We speak mostly about marine sediments rather than freshwater sediments. They occur there also. They occur in marine sediments on the continental margins. And here's a photograph of some gas hydrates taken by Ewan Seuss from Clathrate Ridge. This particular source is now, we suggest this as the major source for the rapid rises in methane. Now, gas hydrates have been called upon to, as Howie mentioned in the introduction, gas hydrates have been called upon to explain rapid climatic warmings or change in the pre-Quaternary geologic past, and increasingly so, primarily attributed to the wonderful work of Jerry Dickens and his colleagues in Michigan initially and then later. But it is ironical that these episodes, such as the late Paleocene thermal maximum, do not have any ice core record to show the actual methane changes. The changes in methane are inferred from carbon isotopic changes. However, this is not the case in the Quaternary. That there is any invoking of a role in gas hydrates in explaining late Quaternary climate change, in spite of the fact that there was much in the behavior of the methane record in the ice cores that perhaps have been predicted for using a source from gas hydrates. There's some irony in that. Now, there are a number of workers who have been involved, and not very many, involved in invoking gas hydrates in climate change. Most of this is occurring in the pre-Quaternary, and there's almost a veritable cottage industry developing in this. And there's a strong consensus that the gas hydrate reservoir does indeed play a major role in climate change in the pre-Quaternary, not so in the Quaternary. And I've mentioned Jerry Dickens, but there's a increasingly large number of workers who are publishing papers on this for the Paleocene, the Cretaceous, Jurassic, Paleozoic, and we'll see more of that, no doubt, in my opinion. The Quaternary is another story, somewhat contentious, and but it was actually predicted somewhat by you and Nisbet in the papers he published 10 years ago, which have been totally ignored, basically. But there's a number of workers like Bill Hark and Paul Seuss, Bruce Buffett, and others, McDonald, Keith Convalden, who have suggested that the gas hydrate reservoir has indeed played a role in Quaternary climate change. Keith Convalden, I think, said it well. He said that the gas hydrate hypothesis, that's what he called it, I believe, is the hypothesis of last resort in explaining climate change in the Quaternary, which I think is a fair statement. So basically, we as authors feel like the Lone Ranger in invoking the gas hydrate in Quaternary climate change, and in fact what we call the hypothesis, we call the clathrate gun hypothesis, which I'll now explain. The main points is sort of a roadmap of where I'm going here in the last 20 minutes or so of the talk, I hope. I better speak more quickly. Is that the gas hydrate reservoir is large, without getting into details. The reservoir was unstable during the Quaternary. It was not stable. It's large, but also unstable. The instability was caused by intermediate water temperature change and in conjunction with sea level change. And it has been associated with slumping and sediment transport down the continental slope. The instability was cyclic. There's a structure to the instability. It wasn't simply random. And that was because it was associated with intermediate water temperature oscillations, which are cyclic and not random, as I'll suggest later in the talk. That there were dramatic changes at the glacial terminations and at the onsets of the BO interstadials, or the warmings. In other words, all hell broke loose at those times. That the methane was released into the ocean atmosphere system. It is indeed recorded in the ice cores, and that this methane is not merely playing a passive role as a response of global warming at these episodes, but it's actually playing a proactive. It's actually playing an active role in fact what we call jump-starting these rapid warmings that occur at the glacial terminations and the VO cycle onsets. And that the gas hydrate reservoir is a critical part of the Quaternary climate system and seems to explain much of the Quaternary climate behavior. Now, those are all of course, quite speculative statements, especially the latter ones, and will require a lot of testing. It's a hypothesis. So here's a concept of the volumes involved of gas hydrates. They're very large. On any measures, they vary according to the author. And basically, if that system is stable, then it's obviously not going to play a role in the Quaternary in any climate change. The methane cannot play a role. But if that is unstable, that is a very large reservoir that has the potential to cause instability in the climate, or at least contribute to the instability of climate change in the Quaternary. Now, the instability of gas hydrates, of course, as most of you will know, is associated with the changing pressure-temperature relationships, pressure being changes in sea level, and temperatures being changes in the bottom water temperatures, so intermediate, in this particular case, intermediate temperature changes at the ocean floor. And that changes the phase so that you can oscillate between the solid phase and the gaseous phase, with clathrates and methane. Now, what this means in terms of the phase diagram is that the most vulnerable and critical part of the instability of the gas hydrate reservoir is in the upper continental slopes, at depths between about 400 meters and 1,000 meters. Depths deeper than 1,000 meters are probably too unstable to participate in any instability during the lake quaternary. So that's the critical part. In other words, is there evidence of instability coming from the upper continental slopes? Now, I've mentioned the pre-quaternary work. This is the carbon and oxygen isotopic record that Lowell Stott and I discovered in 1990, and that shows a basic classic, what I sawtooth pattern. We get a rapid rise in the delta C13, which is interpreted initially by Jerry Dickens and others as representing a massive release of methane into the ocean atmosphere system, and then a decrease back to normality, if you like to call it that, during that cycle, which is about 100,000 years. And this is a huge event, and it's a huge event that's reflected in a very large delta C13 change in the marine record, and therefore it jumps out. It's so big it jumps right out. The quaternary ones are not so large, or they're much smaller, and therefore they don't jump out. If they jumped out, this problem would have been solved years ago. It's more subtle. So in the vernacular, if you like, the clathrate gun hypothesis has three simple aspects to it. It has the ammunition, which is the gas hydrates, which are produced and stored during the cool intervals. It has a trigger, which is the change in, or the increase in intermediate water temperatures during times, especially at low sea level. And then the firing the gun is transferring the methane from the sediments to the atmosphere to basically jumpstart the climatic warmings that mark the deglacials and the onset of the DO cycles. Now, this is basically cyclic, and it's really related to switching of what we call thermohaline circulation, but it's a switching in the character or the dominance of intermediate waters from cold to warm. And so you basically cycle from a stadial state, where the gas hydrate reservoir is relatively stable and accumulating, and there's a decreased atmospheric methane. And then once you switch the thermohaline circulation as it affects intermediate waters, you actually shoot the gun off, which I'm going to show the details of that in the next overhead, because an awful lot happens really quickly here. This leads to a rapid onset of interstadial warming into an interstadial state, where the gas hydrate reservoir is unstable, especially initially, and with an increase in atmospheric methane. Then there's a depletion of the gas hydrate reservoir, leading to interstadial cooling. And then there's actually a switch back to the cool thermohaline circulation. Cool intermediate waters, I mean. Within the brief time of dissociation of gas hydrates, which is caused by the switch in thermohaline circulation, the dissociation of gas hydrates leads to overpressurization in the sediments as a result of the phase change from solid to gas. This leads to slumping, which is reflected by increasing turbidity currents, debris flows, and effluent layers. It leads to a rapid methane release into the ocean atmosphere system that may or may not be picked up as delta C13 spikes in the water column, which is some work that we published earlier this year from the Santa Barbara Basin. This leads to a jump starts to a global warming, which is positively reinforced by a number of other rapid feedbacks, including increased CO2, water vapor, nitrous oxide, and rapid responses such as sea ice albedo, which reinforce that change. Now, in terms of the triggering of this, there is evidence emerging, and there's not much yet, this is early days, that there is an oscillatory behavior in the bottom intermediate water temperatures. This is a record from the Santa Barbara Basin, which we hope to publish one of these years, between 30 and 40,000 years ago. And the green shows the inferred temperature changes of bottom waters, which at this location is 600 meters water depth. And the reds over here in blues are reflecting the sea surface temperature, basically the sea surface temperatures, which are the Dansgaard-Oeschger warm interstadial. So that's warm, cold, warm, cold. You can see quite clearly that there's a cold, warm oscillatory behavior in bottom water temperatures at this location. And we suggest that this is a broad effect that affects many margins, as yet unknown, that's the hypothesis, of the world's continental margins, and acts as the triggering device for dissociation and formation of gas hydrate reservoir. If you look at on the California margin record, this is a site that's on the continental slope proper, not in the borderland province, and site 1017E, Ocean Drilling Program. This is at 1,000 meters water depth, or near 1,000 meters. Again, and we see here the switch between the glacial to the interglacial at the initiation of the Booling, or termination 1A, the first deglacial event. Here we see an increase in temperature of intermediate waters at 1,000 meters water depth, preceding the rapid warmings that mark the sea surface temperatures that mark the beginning of the Booling, or termination 1A. Now, what we suggest in terms of what's happening is that there's basically a concertina effect, or was, and that we're recording this kind of effect here on the California margin, whereby the cold intermediate waters, the Antarctic intermediate water, and the North Pacific intermediate water basically expand their flux rates towards the low latitudes, and then during cold periods and during warm periods, the warmer low latitude intermediate waters expand. So you get this oscillatory behavior, which affects the many margins of the Pacific, and we infer this kind of, we suggest that this kind of behavior may be found on other continental margins and other oceans. So what happens is that we have three basic states, two states that are relatively passive, and one state when a lot happens. So during the glacials and stadials, sea level is low, but there are cold intermediate waters, and that the gas hydrate reservoir is relatively stable, in spite of the relatively low sea level, because a major part of a player in this is not the sea level lowering, but it's the temperature of intermediate waters. During the deglaciations, the onset of the interstadials, the gas hydrate reservoir was highly unstable. And basically this caused instability up the slope, slumping, debris flows, turbidity currents, metalloid layers. And that there was emissions, major emissions of methane into the ocean atmosphere system, which played a role in climate warming. And then during the interglacials, or the late interglacials, particularly, for instance, the middle and late Holocene, when sea level was high, there was still warm intermediate waters, but thermohaline circulation had not switched very, in our case, in the Holocene, 10,000 years, and so there's been a relatively stable system. So you have a very stable gas hydrate reservoir. And that's the problem with this hypothesis, in the sense of selling it, I suppose, or even believing it, is that the modern system is stable. The modern Holocene system is stable. We're not seeing the kind of processes that occurred as far back as 11,500 years ago, or in the earliest Holocene anyway. The system has become stable, and gas hydrates are no longer playing a major role in climate change, but they did in the past. Some of you have seen this. We published this earlier this year. This is a record of the kind of carbon isotopic spikes that can occur during the major methane releases into the water column from the sediments, were inferred to in this paper of ours, in which the entire water column, from top planktonics to bottom benthics, take on a very negative carbon isotopic signal, in which we interpret as very brief spikes of methane release based on the process that I just described. Now, we're moving along here fairly well now, and basically I just want to say there is a literature developing that suggests that there is an association of gas hydrates and landslides or slumps in many areas of the world. this association is now being picked up in different regions, suggesting an association. And I've summarized some of the literature that I've run across in the last few months up in Canada. And these are some of the papers in which there is a suggested association between gas hydrates and upper slope instability in general. And these actually go way back to paper, for instance, Summerhays in 1979. This is in the literature, these suggestions. And that there is developing literature suggesting that not only is there an association, but there are major slumps during deglacial periods. That there was a time, there were episodes of major slope instability during the deglaciation. Now, when I was a student, I always thought that the major slumps would be during the low stand of sea level, and not during the climate change transitions themselves. It was during the low stands. And sure, some of that does occur. There's a paper on the Eastern Mediterranean by Rothwell suggesting a major slump occurring during the low stand of sea level. But it seems like this is emerging that it was times of climate change rather than the low stands of sea level that when this activity occurs. In fact, there's a record, for instance, of turbidite deposition in the Madeira abyssal plain that's published that suggests that turbidite deposition occurred during the climatic transitions. Maslin has studied the Amazon. Maslin and others have studied the Amazon fan and have tried to date, using ocean drilling project legs, the timing of the of mass sediment transport in the Amazon fan, for instance. And what he suggests, I can hardly read these up here on this overhead, it's so bright, is that the last major mass sediment transport event was actually during or very close to the deglacial period at the time of relatively rapid sea level rise. Now, there's also, and more speculative, there's also emerging evidence of extensive clay layers over large areas of the ocean floor, in this case, the tropical Atlantic, that are occurring somewhere close around the deglacial times. This is a paper by Hemming. And what we suggest is that this deposition of clay layer, which has been a bit enigmatic as to what caused it, and as discussed in the Hemming paper, may have been deposited during extensive formation of nepheloid layers. And the nepheloid layers being activated during major upper slope instability as a result of gas hydrate instability during deglaciation. That's speculative and requires a lot of testing. There's another study that was recently published by Bout-Roumezet, and what they suggested, based on clay mineralogical studies in the North Atlantic, is that there, without getting into the details, is that there are clay mineralogical peaks associated with the Heinrich layers, which are the cold periods of the end of the bond cycles, which were formed or laid down by nepheloid layers. And they invoked the activation of these nepheloid layers as a result of actual ice sheet activity at the front of the ice sheets. An alternative hypothesis might be that these nepheloid layers occurring at these specific times resulted from from activation of slumping on the upper continental slopes as a result of the process I've just been describing. I don't know the answer. I'm just suggesting at the end of this talk. I'm very near to the end of the talk. I just want to point out one last thing, and that is the climate behavior or some of the aspects of the climate behavior of the Lake Quaternary. And I think that the the clathrate gun hypothesis is at least consistent with the idea of explaining the sawtooth patterns that occur at the 100,000-year cycle, the bond cycles. These are the bond cycles consisting of several DO events, beginning with with major ones and then decreasing, and then jumping again. And then also the individual DO cycles, which also have the same kind of pattern. There's a pervasive pattern that occurs in climate behavior during the late Quaternary that does cry out for some kind of explanation. So I would suggest that the methane increases are more consistent with a gas hydrate source than a wetland source. Now, this is the kind of behavior, it's very generalized or schematic, the kind of behavior you might predict with the methane production from a gas hydrate source as compared with a developing wetland source. And finally, I want to point out there is another part of the climate record, of the methane record, and in fact the climate record associated with it, that indicates these brief overshoots in the methane associated with the rapid rises. And I've put red arrows showing where these spikes occur. See them here and then here. For instance, on that scale, I'll show you a couple of more examples. This is at the 100,000-year cycle. You can see a very dramatic one here in the Bostock record. There's a very large overshoot. The smaller one there. They're very brief. And then in the grip record of Thomas Blunier's record in Dellenbach and Chapelet's work, you can see there's a dramatic overshoot there. Now, I would suggest, or we would suggest, that this is more consistent with a proactive, a rapid, major emission of methane from a pent-up reservoir, rather than from a passive response of methane from a slowly developing wetland system. That's the kind of behavior that I would suggest is more consistent with a gas hydrate source of methane rather than from wetland source of methane. In conclusion, so there are some of the conclusions. I don't want to read them all in detail, but we would suggest that the wetland ecosystems were insufficiently developed during the last ice age and at the last glacial termination to produce the large rapid methane emission rate that occurred at the last glacial termination, the onset of the DOs and interstadials. Instead, we suggest a gas hydrate methane source is likely for the rapid methane increases. The gas hydrate reservoir exhibits a history of instability during the late Quaternary. This instability appears to have been episodic. The episodicity appears to have been largely modulated by temperature changes of intermediate waters with this kind of behavior, as I won't read it. The upper continental margins were unstable. They were slumping during the warm periods, particularly the early parts of the warm periods, and they triggered mass sediment transport, debris flows, etc. The gas hydrate reservoir is a key player in late Quaternary climate change. Gas hydrate methane represents a stored energy source, and the release jump-starts the rapid warmings. It doesn't do all the work, but it jump-starts the rapid warmings. And that the clathrate gun hypothesis appears to be consistent with much of, not all, but much of late Quaternary climate behavior. Thank you very much.